Welcome to Sundar's lecture. This is lecture number 15, and in this lecture we are going to see logic gates, basic logic gates, and what are all the things we can make a basic logic gate into do multiple things, or with one gate we can implement another gate. With a combination of some gates we are going to get a universal gate. Those kind of things we will see, and we try to implement the logic gates for building the Boolean expressions, right? To build the Boolean expressions, what we are going to do, we are going to use the logic gates, right? So the basics we will see in this class. See, last class we have seen this one, right? We have started with the 5-variable K-map, right? 5-variable K-map, and we have simplified two problems. In one problem, see, I have made a mistake. Anyhow, I have intimated in the comment in my last video. See here, this one is actually D bar, right? This is D bar, right? This is D bar. So if this is D bar, then this answer will be D E bar, right? Because this one we have taken, right? So it will be B bar, D E bar, right? So this is the final answer. I made a mistake in the previous class, right? So now in this class we will see logic gates. First, see what are the three basic operation we have seen in the Boolean expressions. Three basic operations, right? So the first one, it is a not operation, not operation. Number two, it is and operation, and number three, it is or operation. For example, you try to understand, this is these three are the basic operations. If you can perform these three operations, then we can say that all the Boolean expressions can be implemented within the logic gates. That is the whole idea, right? Now what we will do, we will try to draw the symbol of the logic gates and truth table for that particular logic gate. So first what we will do, we will take the NOT gate now, NOT gate, NOT gate, right? So what is the symbol of NOT gate, right? So symbol of NOT gate, symbol of NOT gate, it will be like this. This is the symbol of NOT gate, and if you write this is A, let this be A, and this will be A bar. It will invert. See, if it is a Boolean algebra, Boolean expressions, then you will have only zeros and ones, right? To understand, there is none another zeros and ones, right? So if you give 0 here, it will reflect you 1 in the output. If you give 1 here, then it will be 0. So how will you write the truth table now? That is our ultimate aim, right? So you have just only one input. If only one input, it will be 2 power 1, two number of combinations. So this is 0 and this is 1. And what will be now y? Y means this is y. The output will be y. Y will be is equal to a bar. This is the whole idea. And this will be 1, this will be 0. So this is actually inverting the terms. That is why this is a NOT gate. NOT gate, right? So next one, these are all very basics. You would have already studied in the schools. Anyhow, I tried to remember those kind of things. So this is AND gate. What is AND operation? It is like a multiplication. The basics is multiplication. We can say many other explanation to AND gate. Anyhow, I will tell you. See, what is the symbol of AND gate? Symbol of AND gate. It will be like this. So you just draw like this, and this will be your output, right? This is the input. And if you not only one input, you will have two inputs. So you will have two inputs, so this one, and this is A now, this is B, and Y I can say like A and operator of B. So this is the whole idea, right? So what will be now the truth table? Truth table will be, there are two inputs, so it will be A and then B. So if it is two inputs, how many number of combinations? 4, right? So 0 0 0 1 1 0 1 1. and you try to understand it is not only restricted to two inputs. It can be upgraded to three inputs, four inputs, five inputs. It depends on the application, right? I'm just explaining you things with the two inputs, but you can extend it to the three inputs, right? So now, what is y now? So the AND gate, if you multiply 0 and 0, you will get 0. 0, 1 multiplication 0. 1, 0 multiplication 0. 1, 1 multiplication will be 1. Try to understand, you can say in this way, or you can say it in another way. What is that one? When two inputs are high, then only your AND gate output will be high. If one input is low, then obviously your AND gate output will be low. That is how you can explain the AND gate. And the third gate, third one, it is OR gate. OR gate. OR gate, the symbol of OR gate will be like this. Will be like this. Uh, like this. So this is the output and inputs. Two inputs will be there. Two inputs will be there. One is A, one is B, and this one will be A. Y is equal to A plus B. So it is a OR operator. It is an OR operator. So what will be the output now? So if it is A, if it is B, 0, 0, 0, 1, 1, 0, 1, 1. The same four number of combinations. And what will be now Y? Y will be here. If you add these two, it will be 0. If you add these two, it will be 1, 1. 1, 1 is 1 here. Try to understand, right? So if one input is high, then output will be high. If both inputs are 0, then only your output will be 0. So that is the meaning of an OR gate, right? So now you can perform all the Boolean expression output with these three gates. With these three gates. So what I am saying you, yeah, an important thing, combination of combination of combination of NOT and then OR and AND gate. AND gate is, it is an universal combination. Is universal. What is universal? You can perform all the operations in a Boolean expression with these three gates. Try to understand, right? That is the whole idea. Now, what we will do, we will go for an extended gates like I will say you one gate, that is a XOR gate. Maybe I will write it down as fourth one, XOR gate. Right? What is this one now? And what is the symbol of XOR gate now? XOR gate symbol, it will be like this. Like this. This is the symbol of XOR gate. XOR gate. And obviously it will have A and then B. And I will always write like Y is equal to A XOR of B. What is this one actually? What this XOR of B means is? So that is what we are going to write it down now. So write it as an equation Y is equal to, it is A bar B plus A B bar. This is the actual meaning of this XOR. Right? Try to understand. So if I write the truth table, then only you can easily understand too. So how to write the truth table now? Let this be A and then be, you know, right, only two inputs. So it will be 0, 0, 0, 1, 1, 0, 1, 1, right? This is the input. And what is the Y now? What will be Y? When Y will be high here. See here, when both inputs are inverted, then my output will be high. That's all. Simply you can write like this. So this will be 0 because both inputs are same. This will be also 0, the both inputs are same. And you can cross verify with this truth table. We have already seen this, right? You put you find A bar B and then A B bar, add both things, then what you will obviously get this equation, get this as an output, right? So I'm not going to do that because I have done many a times in my previous lecture. So this is how an XOR gate works. And what we will do now, we will go for the fifth gate, that is XNOR gate. XNOR gate, right? So XNOR gate. And what will be the symbol of XNOR gate? So symbol will be same like XOR gate. same like XOR gate, but you have a not here. But you have a not here, and these are all same. These are all same, and the input will be what? Again it is A, again it is B, and Y will be is equal to A X NOR of B. This is the equation I generally use, and what this actually means, that also you need to understand, right? So it will be AB plus A bar B bar, A bar B bar. So this is how an expression for X NOR will looks like. And you see here, if I write this one AB, it is 0 0 0 1 1 0 1 1, right? So what will be now output? So how XNOR will works now? So when both inputs are same, the XNOR gate will give you the high output. This is 1 and this is 1 because both inputs are same. This is 0, this is 0. And try to compare these two now. Try to compare these two. What I can write here, y will be is equal to A X NOR of B, the whole bar. Am I right or wrong? Because this one, compare these two, it is a bar, right? So what is the actual meaning of this one? So or in other hand also, A X NOR of B is a whole bar. Sorry, I should not write it here. I should not write it here. I can write it here now. Y is equal to A X NOR of B the whole bar. So these two gates are inverted in nature. Try to understand, right? So this is how you need to write the expressions, right? What I can do now, and what I can do now, I will go to the next one, next gate, that is sixth gate, NAND gate. What is this? NAND gate. And the meaning of NAND gate is the combination of AND and NOT gate. For example, see if I can draw like this, right? So this is AND gate, this is an AND gate, and you put a NOT gate here. Put a NOT gate, what you will have? This is actually, if you take AB, if you take this is A, this is B, and what is the output here? It will be A dot B, right? Am I right or wrong? This will be A dot B, right? So here, what I will get now, if I invert this one, it will be A dot B whole bar. Am I right or wrong? So this is how you will get the equation. If I draw an AND gate with an NOT gate, but what we will do, we will combine these two to get a single gate. A single gate. That is the NAND gate. That is the NAND gate. So how I will draw the NAND gate? I always draw like this, and then like AND gate, I will draw, and I will put a NOT here simply. So this is the first input, this is the second input, same. And you know this is A and this is B, and this Y will be is equal to A dot B the whole bar. And if I write the equation or truth table, AB, two inputs, so 0 0 0 1 1 0 1 1, right? Now what I can do now? Y will be what now? Y will be is equal to A dot B whole bar. So opposite to the AND gate, right? So if any one input has 0, then output will be 1 simply. This is 1, this is 1, this is 1. If both inputs are 0, then it will be 0. Right? Can you understand? This is actually opposite to AND gate, right? That's all. And you go to now seventh gate. It is NOR gate. It is NOR gate. So what will be the NOR gate? Simply you would have understood right now because this is R plus NOT gate, right? So this is OR gate, and if I put a NOT gate here, and I will get some output like this, right? So this one and this one is AB, like this is A, this is B, and what will be the output of AND gate? It will be A plus B, right? And what will be this one now? A plus B the whole bar. Am I right or wrong? So this one I can implement with a single gate. So what is the procedure? This will be like this, like this. I can put a NOT here, draw like this. So these two are the inputs now, and this will be A, this will be B, and Y will be is equal to A plus B whole bar. This is a single gate. And if I write the expressions, and we have done many a times, so it will be easy to understand. So 0 0 0 1 1 0 1 1. And what will be the output now? What OR gate will do, if any one input is high, the output will be high. But here it will be 0. It will be 0. When both inputs are high, the output will be 1. So this is the NAND gate and the NOR gate, right? So now what we will do, we will do one different thing. It will help you. Maybe the insight of XOR gates, insights of XOR gates. What I will do now, I will consider an XOR gate. Take an XOR gate. XOR gate. See, what is the principle of XOR gate? We have seen, right? So if both inputs are inverted, then output will be high. That is what we have seen. And now what I will try to do now, maybe I will draw the diagram. I will draw the diagram, right? This is my XOR gate, right? This is my XOR gate. And now what I'm going to do, I'm going to give two different inputs, right? So what I'm going to do now, I will going to give a default 0 this one and to B this one. Can you understand? A which is equal to 0 defaultly. Then what happens now? Now how your truth table will come? This is A, this is B. Two number of combinations, so 0 0. I'm not putting 0 for this one. 0 0 0 0 1 1 0 1 1, right? That is what we would have written. I am not written this one. What I am doing now, A is default 0 here. A is a default 0. And now what will be Y? This is very important to understand. What will be Y now? So these now you see this one, Y will be is equal to A XOR of B. It is going to do. Am I right or wrong? Now if both inputs are 0, then output will be what? 0. If both inputs are 1, the output will be what? 1. If both inputs are same, what will be the output? It will be 0. If both inputs are inverted, the output will be 1. And now what you do now, you compare this one with this one. See this one, see this one. What happens here? Both are same, right? 0 1 0 1 0 1 0 1. And what is now output looks like? What is the output now? Output becomes what now? It is B. It is B, right? Am I right or wrong? Can you understand what I am saying? So this output will be now B. So what is the whole idea here? If you make a XOR gate one pin to default 0, then whatever you are giving in this pin, it will be passed through this gate to the output. It will be passed through this gate to the output. That is the whole idea. And now, maybe if I do another thing now, what I am doing now, you be with me now, be with me. The same thing with a different kind of understanding. Right now, I have these type of input. Now, what I am going to do, I am going to give A is equal to 1, default 1. This is B now. This is B. And you write the truth table as usual. This is A, this is B, right? So this is now 1 1 1 1. And you know the input of B will be 0 1 0 1, right? And what will be the output now? This is Y is equal to A XOR of B, I know that. And Y will be is equal to, Y will be is equal to Y. What is Y now? See here, both are inverted, so it will be 1. Both are same, it will be 0. Both are inverted, it will be 1. Both are same, it will be 0. And now what you do? You compare these two now. Compare these two. What happens? Here it is 0, here it become 1. 1, 0, 0, 1, 1, 0. What happens here? What happens here? What I can write now? Y which is equal to what? It is B bar, right? It is B bar, right? So what I will get it down here. Y will be is equal to B bar. I will be is equal to B bar. Now, what is this gate now? What is this gate? What it is actually performing here? Huh? What is actually performing here? Obviously, it performs not gate operation. Right. Now, can you understand? If you give default 0 to XOR gate 1 pin, and it will pass through this one now. And if you give default 1 to 1 pin, it will make the input whatever you are giving here, 1 to 1 pin. It will make the input whatever you are giving here, 1 to 1 pin. It will make the input whatever you are giving here, 1 to 1 pin. It will make the input whatever you are giving here, 1 to 1 pin. It will make the input whatever you are giving here, 1 to 1 pin. It will make the input whatever you are giving here, 1 to 1 pin. It will make the input whatever you are giving here, 1 to 1 pin. It will make the input whatever you are giving here, 1 to 1 pin. It will make the input whatever you are giving here, 1 to 1 pin. It will make the input whatever you are giving here, 1 to 1 pin. It will make the input whatever you are giving here, 1 to 1 pin. It will make the input whatever you are giving here, 1 to 1 pin. It will make the input whatever you are giving here, 1 to 1 pin. It will make the as a inverted output. So this gate can be considered as a NOT gate. Now what we have done, we have just built a NOT gate using XOR gate. Now tell me one thing. I have already told you what is the universal combination, right? So if a gate or a combination of gate performs NOT gate, OR gate, NOT operation, OR operation, AND operation, then I can call those combination as a universal combination. Now you can take this NOT gate out of the content and put OR gate, AND gate, and an XOR gate. That combination can also perform the universal combination. Am I right or wrong? So that is one type of a universal combination, right? Now, what we will do, I will give you a good idea about another one thing. Another one thing. It will be getting interesting. See, you have to see, you have to know the insights of the gate so that you can understand easily the digital logic circuit. Because we are going to implement the digital logic circuits. Maybe we are going for combinational logic circuits in the next chapter. In that you have to implement some expressions with the logic gates. That is why I'm giving you the insights now. Now what I will do now, I will take a topic like inverted inverted input AND gate. What is inverted input AND gate? Like you know, right? So how will you draw the AND gate? This is AND gate, right? This is AND gate, right? You know this one. You know. And what is the thing here? This is A, this is B, and Y will be is equal to A dot B. You know this one, right? Now what I'm saying you, let give this one as a bar, this one as a bar. Input like this one, A bar and then B bar. And what will be your output now? This will be A bar dot B bar. Am I right or wrong? You are giving A bar and B bar as an input. And what AND gate will do? It will make two and it will make the both inputs with the dot operator, this one. And what is this one now? Y is equal to A bar dot B bar. Apply De Morgan's theorem. Apply De Morgan's theorem. What we can write like A plus B whole bar. And what is this one now? What is this one? What is the output of this one? See here. See here. It is an OR gate, right? So obviously it comes out to be an OR gate, right? This is an OR gate. So what is my point? The inverted input AND gate will be an OR gate, right? So what I can draw now, it is very important to you. Just be with me now. If I draw like this, if I draw like this, what I am doing now? Make this as A, this as B. I have inverted, right? I have inverted here. So what this gate will get now? A bar and B bar. And what I can draw here, what I can write the expression as A bar dot B bar. Can this be drawn like this? Is it so or not? Tell me. Can I draw like this? This gate. What is this one? What is this one? This is actually an OR gate, right? This is actually an OR gate. Am I right or wrong? Huh? I can draw like this, right? If I see anything like this, I can replace this gate with this one, right? So this is the whole idea. So inverted input and gate, it is nothing but an OR gate, right? So what is the next one now? You would have understood, right? You can get my point now. What I am going to do now? Inverted input OR gate. What is inverted input OR gate? Let me draw the diagram first. See, I have an OR gate. I know like this, right? So this will be my OR gate. So this is the input, right? First input, second input, and if I do A and then B, what is the Y will give you now? This will be A plus B. You know this one. And what I am doing now, simply I put a bar here I put a bar here. So what my gate will do now? This will be the output equation. And what is this one implies as? What is this one actually? Y will be is equal to A bar plus B bar. Apply De Morgan's theorem. It will be A dot B whole bar. So what is this one A dot B whole bar? It is an NAND gate, right? So NAND gate. Am I right or wrong? So what is the point here? You have to note it down. This gate will give you NAND gate. So inverted input OR gate is a NAND gate. Is an AND gate, right? So what I can do now, I can draw the diagram like this is an XOR OR gate. Now I may invert the input and I can give this one, and what will be the input now? It will be A, it will be B. So it will be A bar and then B bar. Y will be is equal to A bar plus B bar. I will get like this, right? So now what I can do, I can draw this gate as a NAND gate, right or wrong, right? Now this is A, this is B, and what will be my output now? This is A dot B whole bar, right? This is also A dot B whole bar, right? Can you understand what I am saying? So if I see anything like this, then I can replace this gate with the NAND gate. So inverted input AND gate will give you NOR gate, inverted input OR gate will give you NAND gate. This is the whole idea, right? So we have seen many logic gates basics. So from the beginning, what we have seen today, so we have started with the logic gate basics, and what are the three basic operations are there in Boolean expressions? It is NOT operation, AND operation, and OR operation. So we have seen what is NOT gate, what is AND gate, and what is OR gate. These are all very basics. We have seen those kind of things. And then we have gone for XOR and then XNOR gates. So these two gates are not a straight gate. These are all combinations of AND gate, OR gate, and then NOT gate, right? So we have seen that both inputs are inverted, the output will be high, and both inputs are same and the output will be high, like that. And then we have gone for NAND gate and then NOR gate, and we have seen what is a XOR gate, inbuilt concept of XOR gate. If you give any one input to 0, then what happens? One input to 1, then what happens? And then we have gone for these two important concepts. What is this one? Inverted input AND gate, inverted input OR gate, and inverted input AND gate is an OR gate, inverted input OR gate is an AND gate, right? So what we will do in the tomorrow's class, we will take some expressions and we try to implement those expressions with the gates, and then we will go to the next topic, right? So thank you.